Lesson 18, pulleys and systems. So pulley and system problems. They're going to be kind of unique. We got a few special ways that we're going to do this. Um, and they're going to be this type of thing happening where you've got, let's say, like a 10 kilogram mass hanging from one side of a pulley and a 5 kilogram mass hanging from the other. And you can tell that this thing is going to accelerate down this way, right? Because this is heavier. A few things we're going to do, though, is we are going to assign different directions because the downward acceleration of one means the upward acceleration of the other. So this is going to get a little bit confusing if we just stay with our normal convention of, up being positive and down being negative and left negative and right positive. So we're going to kind of drop that for this case. And what we're going to do is we're going to choose the direction that something's accelerating as being positive. So if we're looking over at this side, it's accelerating downward. So we'd call downward positive in that case. So it really kind of depends on which mass you're looking at here, right? So down on the 5 kilogram side would be negative. Down on the 10 kilogram side, we're going to call positive. So it's the direction of acceleration is what we're going to call positive now. So we are going to assume when these things accelerate too, that they are accelerating at the same pace, right? That the acceleration of this 10 kilogram mass going down is the same as the one going up. If they weren't the same, then the rope would snap, right? They have to be the same. We are going to, the way we're going to do this though, is we're going to calculate the acceleration by drawing a free body diagram for the whole system. And this is a new concept. So if we draw this as the system, you see I've got like 5 plus 10 written here. That stands for like 5 kilograms plus 10 kilogram mass. So the 5 plus 10 kilogram mass, as if they were one thing, right? It's just one system. We're going to say that it's being pulled downward with force of gravity of the 10 kilogram one. And it's like it's being pulled upward with the force of gravity of the 5 kilogram one. Hopefully that made sense. It's like it's one thing that's being pulled up with the 5 kilogram one and pulling down with the 10 kilogram mass, right? Okay. So the net result here would be just the force of gravity plus that one, and really you'd be subtracting them, right? And then what we're going to do is figure out acceleration just using Newton's second law. F is equal to ma, or a is equal to f over m. And you'd add the forces just from this, but then you'd also have the combined mass because it's the masses of the system. This might make a bit more sense when we start actually doing these problems though. So we'd figure out the acceleration using the system. When we figure out the tension though, we're going to do it a little bit different. When we figure out the tension, you're going to look at one of these masses like independently. So just look at it as it is on its own. So then you look at that. Did I choose 10 on this one? 5. So it doesn't matter which one you look at, but if you were looking at the 5 kilogram one, you look at that just on its own. Kind of ignore the 10 kilogram one for now, right? So you'd look at that and you'd have a FG for the 5 one going down, and then you'd have a force of tension going up. And that's the free body diagram we're going to do to figure out the tension in the rope. Yeah, so that's our formula. And then what you're going to do is figure out what the net force is using that acceleration that we just found above. So then if you do that, we can just rearrange this for t and solve. So this will make more sense when we start going through some though. All right, so example 1, a 30 kilogram mass is connected over a pulley with a 20 kilogram mass. What's the resulting acceleration when the masses are released? What is the tension in the rope? So just what we've been talking about. So I think you guys should. Oh, I'm frozen. All right, I figured it out. Draw a good diagram, kind of like this one, right? And what's going to be helpful is if you figure out your force of gravity on each of those masses first. So the force of gravity. And when it says G30, it's talking about it's just a way of showing that it's talking about the 30 kilogram mass. Same with this one, G20. So figure out your force of gravity for both of those first is what I suggest. And again, we're going to call positive the direction that the thing is accelerating. So it's going to be accelerating down on the left side. It's going to be accelerating up on the right side. So that's the conventions we're using. To calculate the acceleration, we draw a free body diagram for the system. That's what this one's about, right? So systems. Write the net force relationship and use Newton's second law. So for this system, this is kind of the hardest bit, or the toughest bit here. Our free body diagram, including the 30 and the 20 kilogram mass, we're going to say it's accelerating downward with the 30 kilogram mass, right? It's going down, right? And we're calling that positive on this side. So that's going to be 294, and that's going to be positive because now down's positive. And the 20 kilogram mass, the one that was responsible for it, for this side, that's going to be pulling this thing up at negative 196.2, and now negative's up, right? So if we're going to figure out the net force of this thing, it's going to be the force of the 30 kilogram, force of gravity of the 30 kilogram one, plus the force of gravity of the 20 kilogram one. So positive 294 minus 196.2. The net force is going to be going down at 98.1. And it's down because it's positive. That's the conventions that we're using, right? Okay, once you know that, we just need to use Newton's second law. Force is equal to mass times acceleration, or acceleration is equal to net force over mass. And just the thing to remember here, though, is this mass is the mass of the system, right? So it has to be the mass of both of them combined. So just don't forget about that. And then we get an acceleration of 1.96 meters per second, and that's going down because down's positive. All right, now tension. So like part two of these, they're done a little bit different, right? Now to figure out tension, we just look at one of the masses. It doesn't really matter which one we look at. Probably going to be easier if we look at the 30 kilogram one, just because we're calling down positive. So we can just kind of stay with the conventions that we did before. If we were looking at the 20 kilogram mass, we're calling up positive. See, that just might confuse you, is the only reason I think you probably want to do the 30 kilogram one, just because down's positive, just like what we've been doing. Okay, so then just looking at that, this is now just 30. We're looking at just the 130 kilogram mass. The net force of this thing, of just the 30 kilogram one, is going to be the tension plus the force of gravity pulling down. Rearrange this for tension, and you're going to get a formula that looks like this. We're good for the force of gravity of the 30 kilogram one. We figured that out first, right? We figured that out right up here. So that's that. So we got that one already. We don't really have the net force, though, but we can figure that out simple, and that's what has been done over here. So F net is going to be equal to mass times acceleration. Our mass is 30 kilograms. Our acceleration is what we just found in the part above, right? We got that from the first part. So our net force is going to be 58.9 newtons, and it's positive, so it's down. Remember? Okay. I'm probably saying that too many times. Now just fill in what you know. So positive 58.9 newtons minus positive 294.3 newtons, because it's going down as well. So this is going to be negative 235 newtons. Negative means up, which makes sense. The force of tension is up. So the magnitude of the tension is going to be 235. Okay, moving on down. Another type. So a 200 kilogram mass rests on a surface, that's this one, which has a coefficient of friction. Oh, we're bringing friction into this too now. It is connected to a 100 kilogram mass over a pulley as shown in the diagram. When the masses are released, what is the resulting tension in the rope? So for this one, like I was saying, we want to get a free body diagram for the entire system, and that's where we're going to end up. But you can see that we don't have a friction force yet, right? We don't know what this one's pulling back with. We don't actually know yet. So step number one is we got to figure out what that friction force is. So we need to make a free body diagram just for this box first. And that's what's drawn below here, right? This one down below it is a free body diagram for that box. So if we do that, we can figure out what the force of gravity on the box is simply by multiplying by 9.81. So then we get that for the force of gravity. That is also going to be equal to our net force, right? Or not net force, our normal force on this one. So the force going back up again. Okay, so we're good there. The force of friction is just going to be equal to the coefficient of friction times that. And then our force of friction is now 490.5 newtons. So there, we've got a bit more information on our 200 kilogram box or block. Now, if we're looking at the 100 kilogram block, this one's going to be a little bit more straightforward. We're going to call down positive though, because that's going to be the way that we're going to assume this thing is accelerating. Well, it's the only way I could. It's not going to go back up the up the ramp. So we're going to call down positive, and Fg is going to be 100 kilograms times 9.81 meters per second. So 981 newtons down. Okay, so we've got our two forces. This one's pulling with 981 newtons. The other one's 490 newtons. So now we can make a free body diagram for the system. So if we look at the system here, it was the worst spelling or way to write system ever. Anyway, if we look at the system, this is for the 100 and 200 kilogram thing or mass. Then we can think about this thing as one thing pulling this way and pulling back with a certain force of friction. And it's going to be pulling this way with whatever the force of the 100 kilogram mass was, which was 981 newtons, right? So Fg 100. Okay, so now if we figure out the net force of the entire system, that's going to be positive 981 newtons, because remember we called that the direction that it's accelerating, so it's accelerating in that direction. And then plus negative 490.5 newtons. That's the force of friction pulling back. So the net result of this is going to be 490.5 newtons. All right, now that you know that, we've done all kind of the hard work. Now we just need to use our Newton's second law, plug in our numbers, not forgetting that we have to add both masses together when we talk about this mass. And then we get positive 1.635 meters per second squared. And the only reason why we left it with extra digits there is because we're going to use this number in the part below. So in the part below here, we're going to have, so it says calculate the tension. We need to look at just one of the masses. So we're going to choose the 100 kilogram mass, so the one going up and down. We could have chose the other one too, though. It would have still worked. So the net force is going to be equal to the force of tension plus the force of gravity pulling this thing down. Rearranging this, the force of tension is going to be equal to the net force minus the force of gravity. We know the force of gravity on that one. We don't know the net force yet, but we can figure that out over here. So that's going to just be equal to the mass times the new acceleration that we just found. So now we know the net force. Plug that in there. Plug in our force of gravity of the 100 kilogram mass. And then you end up with a force of tension of negative 817.5 newtons. And negative means it's up, which makes sense because force of tension is up in this case. Okay, hopefully that made sense. But now we're going to go to another one, another style. Okay, so for the system below, find the acceleration of the masses if the coefficient of friction is 0.12. So we've got two masses here. We got this one and we got this one. We need a free body diagram for both. And again, the reason why we got to do it for each one before we do the free body diagram for the entire system is because I don't know what the force of friction pulling this one back is. And I don't know what the force of friction pulling this one back is. I need to know those if I'm going to do the free body diagram for the entire system. So if we draw this out, we can see that this free body diagram is going to have the force of friction pulling back, the normal force going up, Fg going down, and it's going to have the force of tension of this rope pulling it forward too, right? That's going to be the same as the force of tension of this rope pulling back. Okay, so just looking at this box A, I can figure out that the force of friction is 11.8 just by doing what we've done a few times. So look through that, make sure that makes sense, and then we can figure out. Well, let's go through this free body diagram too. You can see that I've got the force of friction going to the left here, and the force of tension. I've got two things going back, right? Friction's holding it back, and so is the tension from the other box pulling it back. So I've got two things happening there. Normal force, force of gravity, and I've got 100 newtons pulling it forward. So we can figure out our force of friction again by doing what we've done before. And now that really should be all we need for that first part, because if you think about it, the tension of this one canceled out with the tension of that one. So we really just had the force of friction of both blocks holding us back, and then the force of the 100 newtons pulling us forward. So that's it. So the free body diagram for the system is going to be those two forces of friction pulling us back, and then 100 newtons pulling us forward. So we can have a formula for our net force as just the two forces of friction plus the force applied. And if you do that, you end up with 64.7 newtons. That's our net force. And then we can figure out our acceleration from that. Okay, so hopefully that made sense. I'm going to carry on with the practice problems in the next video.